HEFESTO is a project which is aimed at developing and demonstrating a new multi-layer concept which is aimed at protecting carbon fiber structures against fire events and to protect them in operational conditions against thermal events. The HEFESTO project also covers the redesign of aircraft structures today made in metal into carbon fiber reinforced plastics in order to take advantage of the low weight and fatigue resistance of these materials, while complying with the fireproofness requirements of aerospace industry, which are required for certain parts in the aircraft. The fire conditions imposed by aviation are contemplated, among others, in the CS29 standard. In particular, the multi-layer protective coating should be able not only to avoid the burnout of the carbon fiber reinforced plastic part, but to keep it below safety temperatures, during sufficient time not to diminish the mechanical strength of the structure, all in the presence of heavy mechanical vibration. The shot multi-layer configuration should appear to behave optimally in terms of thermal isolation, fireproofing, and firefighting requirements. It also should be of easy application, low cost and weight, while maintaining its fireproof effectiveness. The project also looks at the process of removal and replacement in the case of material degradation or damage under operating conditions in anticipation of maintenance-related problems as well as long-term environmental deterioration. The test setup mounted in AIN complies with the ISO 2685 of the aerospace industry, consisting of exposing the samples to a flame of 1100 degrees C during 15 minutes. The coupon is then exposed to a flame of an impinging diameter of at least half of the area of such coupon, placing a temperature of 1100 degrees C and a heat flux of 116 kilowatts per square meter directly onto the surface of the coupon. In order to make sure that we reach the correct values, a heat flux gauge and temperature monitoring setup has been constructed and tested. The coupons are then monitored during its exposition to the flame using a set of thermocouples, which can be up to 12, located at the interface between the carbon fiber material base plate and the multi-layer protective coating. A temperature monitoring as a function of time has been measured using a data recorder. A signal adapter circuit is used to convert the signal into temperature recording datasets. Preliminary calibrations and adjustments are made using simple lab flames.
The project has been developed along two particular lines. One, in a market search for particular materials that might be useful for the project, and in parallel, an engineering study of the engine deck area. The study of materials which might be appropriate, which is really the nucleus of the project, consisted in doing a survey of materials which are easily available and really cheap in the market, which could be combined in different ways to produce something which had the benefits of one material and the other at the same time, above all in conditions of thermal isolation and fireproofing. The other part of the project, which is running in parallel, is the engineering office study of a helicopter engine deck, which is traditionally made in titanium. The new redesigned engine deck is made of carbon fiber and has to serve exactly the same function in terms of structure and from a fireproofness point of view. The redesign consisted in applying the same loads to the carbon fiber structure so that it would resist in the same way, and the final product visually is quite similar to the original titanium one, although it has some limitations because of the actual properties of carbon fiber material. One very important part of the project from an engineering point of view, for obvious reasons, was the interpretation of the response of the new materials to a fire situation. What we did in the engineering office was to use programs which are for simulation of fire to try and reproduce the conditions that we think are happening in the context of the helicopter in a fire situation. The modelling that we did is much simpler than you would do for a real event, but then we were basing ourselves in the initial studies related to simple tests that we were doing with the materials on pieces of carbon fibre, which were covered of about 200 millimetres by 200 millimetres. The initial part of manufacture consisted in producing carbon fibre specimens, which were square of 200 by 200 and then 500 by 500 millimetres. The full-scale test, however, generated new problems which were completely different, as the structure is much more complicated. Also, the layers that we were applying, the final combinations in themselves, were relatively complicated, and putting them together in one piece of plastic produced new design problems which we eventually overcame. However, they were all very interesting. The most interesting of all is in the second specimen, which is dedicated to investigating some details which are more close to real life. We have included some metal fittings which we have had to mount on little ceramic feet to try and avoid the heat being transmitted through the protective coating to the plastic. We are waiting to see how well this works in practice. At the end of the project, a full-scale test will be carried out on a specimen which is extracted directly from a helicopter engine deck, and the ISO 2685 fire test will be applied, hopefully successfully.